If no questions, we are going to describe how we can generalize finite element for in 2 and 3 dimensions. That's probably the hardest one to explain. So let's get started. So finite elements, the way it works in 2 and 3 dimensions is it follows a similar approach to the one-dimensional problem. First, we have to we have to translate the equation into its weak form. So for example, let's consider a very similar equation from what we have considered in the one-dimensional case. So the x derivative plus y derivative of the same function u plus f is equal to 0. Okay, inside a domain called omega. Let's say this is the domain, and again, the surface, the boundary of the domain. Well, in 3D that will be the surface. In 2D, it's just a boundary of the domain. Let's say u at u is equal to 0 at the boundary. Okay, so that's probably the simplest equation to explain in multiple dimensions. So if we have this equation, we have to multiply this equation with a test function v, right, to get this into a weak form. So once we multiply this equation, we get something like this. So if this equation holds true for any x, then when we multiply this equation with any function v of x, it is still true, right? Still equal to 0. And then if we integrate the whole thing over omega, it should still be 0. And it should still be 0 for any differentiable v that satisfy the same boundary condition, v equal to 0 at the boundaries, right? Okay, so now we have the integral form. It's time to use integration by parts to transform this into its weak form. And the integration by parts, now we have this in 2D, right? Really is not that much different from the integration by parts in 1D. So let's discuss this a little bit more rigorously. So the integration by parts in 2D is like that. It starts with, again, it actually starts with 2 and 3D. It starts with the Gauss's theorem. It starts with the fact that if you take the divergence of any vector, let me just call the vector, we already used the f here. Let's say the vector is h, right? The divergence of h over dx, or I mean, dx is dv in 3D or ds in 2D, is equal to a boundary integral of the outward normal dot with the same h, ds, right? The ds is a line integral in 2D and the surface integral in 3D. Now, because the h can be any vector, it can also be a scalar function times this vector function, right? I mean, this is also true. So G, a scalar field or function, H is a vector field. Okay, so now we can use, we can try to expand this, right? If we expand this, what we get is integral of, okay, so if you are not familiar with vector calculus like this, a neat trick is the following: use the Einstein's notation, right? So the divergence of GH is actually can be written as partial partial xi of g times hi, where if I have a repeated index, it means I'm summing over I equal to 1, I equal to 2, I equal to 3, if there are 3 dimensions. Okay, so that can be expanded into 2 terms. One term is hi times partial g partial xi, right? Xi, x1, x1, x2, x3 is actually x, y, z in 3 dimensions, plus g times partial hi partial xi. So now we can write this back into vector form. So this is, g is a scalar function, right? So partial g partial xi, when you look at the 3 components, is actually now really the gradient. Agreed? And h, being a vector, is now dot producted, right? Because it's repeated, the indices means sum over the indices, is h dot the gradient of g. And the second term is g, the scalar function, times, what is this? Yeah, what is this in vector form? Summing over repeated indices. Well, again, this is the divergence of the vector field H, right? The divergence of H. So if I expand this, which is here, I get 2 terms, H dot with gradient of G dx plus G times divergence of H dx. That is equal to the boundary terms. And this is now very analogous to the derivation of integration by parts in 1D, except for whenever I encounter the dot product of a vector with a gradient, I can translate it into a boundary term minus the product of the scalar function and the divergence of the vector function. Essentially, I can take the scalar function out of the gradient and then put the vector function, put the corresponding vector function into a divergence. Or I can do the other way. I can pull a vector function out of a divergence and put the scalar function outside of any derivatives inside a gradient. Right? So this is really the integration by parts, and you can use it both ways.